A3 T63 01. How much cooling is required to turn 100 pounds of steam at 214 degrees Fahrenheit into ice at 30 degrees Fahrenheit? This is essentially a mathematical calculation using the heat transfer formula. But we have to realize that when you cool steam all the way down to ice, we're removing BTUs of heat from it in both the sensible and latent varieties. So let's start at the top right-hand corner of this very standard temperature versus enthalpy graph of water, or H2O, right? Up here we have steam, and as we move down the curve, we end up all the way back to ice at a temperature lower than 32 Fahrenheit. And I'm going to fill in the chart with the numbers from our question, identify where we're removing sensible heat and latent heat, and then all we got to do is calculate how much heat is being removed each step of the way, right? In other words, how much cooling is required. So let's start at the very top right-hand corner where we have steam. And we know that in our question, the steam is at 214 degrees Fahrenheit. So I'm going to write 214 right there. The first thing we have to do is remove an amount of sensible heat from that steam, which will cause it to cool. It'll cause it to cool right down to its condensing temperature at 212, right? So we remove sensible heat energy from the steam at 214 and we reduce it to 212. Then what we want to do is continue to remove heat energy from it. But the heat energy that we're going to remove from something which is now 212 degree steam into 212 degree water is going to be the removal of latent heat. So we're going to cause a change of state. So we continue to remove more heat energy from our 212 degree steam, and this happens at a constant temperature of 212, until eventually we change all the steam back to water, and that's at 212 degrees Fahrenheit. Once again, because we're continually removing heat from it to get to our final destination of ice, we're going to remove more sensible heat. So we continue to remove more BTUs of heat energy, which causes a further reduction in the temperature of the water at 212. And we're going to continue to reduce its temperature until we get to just the first point of freezing at 32 Fahrenheit. Now, once we reach that 32 Fahrenheit point, freezing can begin. In other words, a change of state. So we're going to continue to suck more latent heat, BTUs, out of it at 32 Fahrenheit. And that'll happen at a constant temperature of 32 Fahrenheit until we get that change of state, once again, from a complete liquid to a total solid. So right here on the curve, we finally have solid ice. But the ice we're interested in isn't at 32 Fahrenheit. It's at 30 degrees Fahrenheit. So that means there's an implication that we remove a little more heat energy from it, which will be of the sensible variety because it causes a reduction in temperature, which will finally take us down to 30 degrees. So there's two formulas we got to know. And then we can just start adding up our heat contents, right? We got heat being removed here, 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 and here. And we can identify them as steps. We can call this step 1, step 2, step 3, step 4, and step 5. I'm just going to get my calculator ready because we're going to need that very momentarily. So let's start with step 1. We are basically removing sensible heat energy from steam and cooling it from 214 to 212 so that we can then start liquefying it or condensing it. So step 1 means that we're going to use the sensible heat formula of Q, the amount of BTUs of heat energy removed, is going to equal the specific heat of steam, which is 0.5 BTUs per pound, right, times the change in temperature. And the change in temperature here is 2 degrees, right? We're going to go from 214 to 212, and that means we got to remove 0.5 BTUs per pound of this particular amount of steam in order to get it to 212. But bear in mind, we have 100 pounds of the steam. So we've got 0.5 BTUs per pound being removed from 100 pounds and we're reducing it 2 degrees. So let's quickly do the math on step 1. We've got 0.5 times 2 times 100. And I'm going to be pretty meticulous here. We end up with 100 BTUs. So let's just circle that, because that's our first amount. I mean, once we calculate each of these steps, we just have to add them up and it gets pretty simple. So let's go to step 2 now. In step 2, what we're doing is continuing to remove heat, but in this case, there's no change in temperature. What we do know, though, is that when you remove heat energy from steam, which causes it to condense back to water, you're going to be removing a whopping huge amount of BTUs per pound. If you recall, you're going to be removing about 970 BTUs per pound, right? Times 100 pounds of that actual steam being condensed. So that is a big, big number. 970 BTUs per pound times 100 pounds. It happens at a constant temperature, so we don't have to worry about any changes in temperature. There's no delta T. So this is a pretty straightforward multiplication, but I'll still use my calculator so I don't miss any zeros. It looks like I'm going to have 97,000 BTUs being removed in step 2. All right, let's go to step 3. Step 3, we're back to removing sensible heat energy, but this time from water. So the specific heat of water is 1 BTU per pound. It's different than steam. So we have 1 BTU per pound, 1.0, right? Times a change in temperature. Now our change in temperature is from 212 to 32. So I need 212, subtract 32, which is 180 degrees. Okay, that's our delta T. And of course, we still have 100 pounds. So we got to carry that 100 pound multiplier in every step of the way here. So let's multiply that out. We got 180 times 1, which is itself, times another 100 pounds. So we got 18,000 BTUs being removed in step 3. We're getting close to the finish line here. Step 4. Step 4, we are back to latent heat energy changes, right? Latent heat energy changes when you're talking about water being frozen and changing state back to ice, 144 BTUs per pound. So we got 144 BTUs per pound. Those are constant numbers for water, and we have 100 pounds. So that is going to equal 144 times 100. I'm just checking my math once again. 14,400 BTUs in step 4. So we're very, very close now. We're up to step 5. How much heat energy is being removed in step 5? We're back to removing sensible heat. So when you're talking about taking ice at 32 Fahrenheit and reducing it to ice at 30, we're back to a specific heat of 0.5 BTUs per pound. So we got 0.5 BTUs per pound of ice times a change in temperature of 2 degrees, because we're going from 32 to 30 Fahrenheit. So our delta T is 2 degrees. And of course, we have 100 pounds. So we're going to add all that up. Hopefully I don't run out of room on the screen. 0.5 times 2 times 100 is equal to 100 BTUs. So 1 plus 2 plus 3 plus 4 plus 5 should give us our correct answer, or at least very, very close. I'm going to add those up. I got 100 in step 1. I'm going to add to that 97,000 in step 2. I'm going to add to that 18,000 in step 3. I'm going to add to that 14,400 in step 4. And finally, 100 BTUs in step 5. So when all of these are added up, the total is equal to, by my calculation, 129,600 BTUs. So we know our answer is going to be B, 129,600 BTUs. The equations we were using For sensible heat change, you have Q equals the specific heat of whether it's ice or steam, right? The specific heat, changing temperature. So we're going to multiply that by delta T, the change in temperature, times the weight. We use that formula for step 1, and we use that formula for step 3, and we use that formula for step 5. But steps 2 and 4, we used a very simple formula, which was the latent heat energy changes, which is going to be Q is equal to, I'll just slide that up just a touch, the specific heat, which is 970 BTUs if you're going water to steam or steam to water, 144 BTUs if you're going from liquid to ice or ice to liquid. So we got the specific heat, basically, which is how many BTUs per pound are required to change state, and then times the weight, W. Little bit of calculation. The secret to answering the question correctly is to take your time and stay organized. It's very easy to miss a step. If you get a question like this on the exam, I highly recommend drawing a curve like you see here, okay? It's very easy to remember. You start with ice at the bottom left, and you end up with steam at the top right. Go through your steps with the heat transfer formulas, and this should be a gimme on the test. Good luck with that one.